All right, let's dive in. Today, we're going on a tour of what is, without a doubt, one of the most amazing pieces of engineering in the entire universe, your cardiovascular system. We're going to build it from the ground up right here. Just let that number sink in for a second. 2.5 billion times. That's not an exaggeration, that's the average workload for your heart. It's an engine that kicks on before you're even born and never, ever takes a day off. Not once. So, how on earth is a machine like that even possible?
So, to wrap our heads around this, let's use a simple analogy. Think of it like this. The heart, that's your high-performance pump, the engine at the center of it all. And the blood vessels? Well, that's the incredibly complex dynamic highway system that delivers all the fuel and carts away all the waste. The pump and the pipes.
And that is the big question for us today, isn't it? How is this thing actually built and what gives it its spark? We're going to answer that by building it ourselves, starting from the tiniest parts and working our way up to the whole system.
Okay, first things first. Before you can build an engine or a highway, you need the workers. You need the specialized, microscopic crew that does all the heavy lifting, all the building, and all the maintenance.
To build this system, you really just need to know about 3 cellular superstars. First, you've got your cardiomyocytes. Think of these as the muscle, the raw power for every single pump. Then you have endothelial cells. They form this super thin, delicate inner lining of every single blood vessel. And finally, you've got smooth muscle cells. These guys are the tuners, squeezing or relaxing the vessels to control everything.
Now I want to zoom in on that endothelial cell for a second. It might only be a single layer of cells thick, but you could argue it's the single most important regulator for the health of your entire vascular system. It's a huge deal.
Yeah, these cells are not just a passive wallpaper. They are the active managers of the entire highway system. I mean, look at this job description. They're the bouncers at the club door. They're the traffic controllers telling blood where to go. They're the first responders to inflammation, and they even manage blood clotting. Bottom line, if your endothelial cells are healthy, your cardiovascular system is likely healthy too.
So, we've met the workforce. Now, let's see what they actually build. We're moving up from the cellular level to look at the actual hardware, the pump and the pipes.
You know, if you were to slice an artery in half and look at it, you'd see this really elegant 3-layered structure. On the inside, you have the intima. That's our critical endothelial lining. In the middle, you've got the media, which is where all those smooth muscle cells live, doing their squeezing and relaxing. And on the outside, there's the adventitia, this tough protective coat.
And here's a little detail that I think is just mind-blown and shows you how complex this is. The walls of your biggest arteries, like the aorta, they're so thick they actually need their own tiny blood supply to stay alive. It's a network called the vasa vasorum, which literally means the vessels of the vessels. Yeah, the highways need their own little access roads. How cool is that? Okay, so the hardware is assembled, the pump is built, the pipes are laid out, but nothing's moving yet. We need power. We need the spark that brings this entire engine to life.
The power for every single one of those 2.5 billion heartbeats? It all starts right here, deep inside the heart muscle cell, at the level of the sarcomere. This is the fundamental microscopic piston in our engine. It's basically made of 2 little protein filaments, actin and myosin, that are designed to slide past each other.
And here's how that tiny piston fires. It's a beautiful 5-step dance. First, you get the spark, an electrical signal. That triggers a flood of calcium. The calcium then allows these little myosin heads to reach out and grab onto the actin. Then comes the pull, the power stroke, fueled by our body's energy molecule ATP. And that's what contracts the muscle. Finally, everything resets. The calcium gets pumped away, and the muscle relaxes, instantly ready for the next beat. All of that in a fraction of a second.
So, our engine's running, it's beating away, but, your heart doesn't just have one speed. Sometimes you're asleep, and sometimes you're sprinting for your life. So how does it go from idle to full throttle? Well, the heart has a few main control knobs it can turn. The first one is called preload. This is basically how much the heart muscle gets stretched by blood filling it up right before it beats. The rubber band analogy here is perfect. The more you stretch it, the harder it's going to snap back.
Okay, control knob number 2 is afterload. If preload is the stretch, afterload is the resistance the heart has to push against to get the blood out. Think about trying to push open a really heavy spring-loaded door. That resistance you feel, that's afterload for your heart.
And finally, there's contractility. Now this one's different because it's totally independent of stretch or resistance. This is the raw, intrinsic horsepower of the muscle itself. To go back to our analogy, it's not about how far you stretch the rubber band, it's about the quality of the rubber itself. Is it a brand new, powerful band or an old, flimsy one?
So what happens when you put it all together? Well, look at this. It's absolutely dramatic. When you exercise, more blood comes back to the heart, which cranks up the preload. Your body releases adrenaline, which boosts contractility. And the result? You go from pumping about 5 liters of blood a minute at rest to 20 liters, or even more. That's a 4-fold increase in power, just by turning these dials.
And that's really the key takeaway here. These 3 things, preload, afterload, and contractility, they aren't working in isolation. They're in this constant, beautiful, dynamic dance with each other, a feedback loop that tunes the engine's performance perfectly to what your body needs, moment by moment.
So we've just built this incredible machine. It is designed for stunning performance, for unbelievable resilience. But that very fact raises a really important question. What happens when this perfect, delicate balance gets thrown off? Because understanding how this system is built, well, that's the absolute key to understanding what happens when it breaks.